Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Hello. This problem is similar to other mass spectrometer problems, but we're given constraints about the physical size of the mass spectrometer, and we need to consider the circular motion happening within that mass spectrometer. So let's get a visualization of what's happening here. We have a region of space that consists basically of our mass spectrometer, and we have a magnetic field inside that space, everywhere inside that space, going into the screen. So we have a magnetic field into the screen here. Now, if a proton enters, so MP, right, we have something of plus E charge, there's our charge. If a proton enters this region here with some velocity v, what's going to happen is it's going to follow a circular path. But we're asked to find what the magnetic field needs to be in this mass spectrometer such that this proton just doesn't hit the other side of the plate of the mass spectrometer. So what does that mean? That means the circular path is going to have to look something like this, right? The radius is going to have to just barely touch the other side of the mass spectrometer as this particle zips around in a circular motion. What does that mean for the radius of this path? Well, if you look at the physical constraints of our system, we see that the radius of our circular path of our charged particle or proton here must be the width of this mass spectrometer. And that's the key piece of information that we need to know, because we know from our equation for a mass spectrometer that the radius of that path is going to be given by the mass of our particle multiplied by its speed in the mass spectrometer divided by the multiplication between the charge of the particle and the magnetic field through which it is traveling. So if we want to find the magnetic field that we need to cause such a radius of circular motion, we just solve for our magnetic field, which means we get an equation like this. So we know what the radius of the path must be because it must be the width of the mass spectrometer in this case. And everything else is given to us. We know the speed that the proton enters the mass spectrometer, and we know the charge and mass of this particle because it is a proton. Okay, so let's just plug in everything we know and get the answer. So the magnitude of the magnetic field we need here is going to be given by the mass of our proton, 1.6 times 10 negative 27 kilograms, multiplied by how fast it's traveling in the mass spectrometer, 3.5 times 10 to the 6 meters per second. Then we're going to divide this by the elementary charge of a proton, 1.6 times 10 to the negative 19 coulombs. And then we multiply this by the radius of the path, which must be also the width of this mass spectrometer, 0.23 meters. Plug all that into our calculator, and we get our answer that the magnetic field must be of magnitude 1.16 Teslas in order for this proton to just barely not hit the side of our mass spectrometer.